Good day, everyone. I'm Bea Juanola, and together with Francine Ciara, we are diving into the fascinating world of nuclear fusion, a game changing energy source that could reshape our future. Fusion has the potential to provide an abundance of clean and sustainable energy, and in the next few minutes, we'll explore the science, opportunities, and challenges behind this revolutionary technology. Welcome to our journey into the world of nuclear fusion energy. The coverage of this video will be the following subtopics: the potential role of nuclear fusion in sustainable energy for the 21st century, the global, regional, and national policies on nuclear fusion energy, the basic concepts and principles of nuclear fusion, state of the art and emerging technologies, sustainable attributes in terms of environmental and social issues, the sustainability attributes in terms of economics and energy market, and finally, the research and development opportunities to improve technological viability and sustainability attributes. And before we get started, let's watch a video on everything you need to know about nuclear fusion.
The fundamental currency of our universe is energy. It lights our homes, grows our food, powers our computers. We can get it lots of ways: burning fossil fuels, splitting atoms, or sunlight striking photovoltaics. But there's a downside to everything. Fossil fuels are extremely toxic, nuclear waste is, well, nuclear waste, and there are not enough batteries to store sunlight for cloudy days yet. And yet, the sun seems to have virtually limitless free energy. Is there a way we could build a sun on Earth? Can we bottle a star? The sun shines because of nuclear fusion. In a nutshell, fusion is a thermonuclear process, meaning that the ingredients have to be incredibly hot, so hot that the atoms are stripped of their electrons, making a plasma where nuclei and electrons bounce around freely. Since nuclei are all positively charged, they repel each other. In order to overcome this repulsion, the particles have to be going very, very fast. In this context, very fast means very hot. Millions of degrees. Stars cheat to reach these temperatures. They are so massive that the pressure in their cores generates the heat to squeeze the nuclei together until they merge and fuse, creating heavier nuclei and releasing energy in the process. It is this energy release that scientists hope to harness in a new generation of power plant, the fusion reactor. On Earth, it's not feasible to use this brute force method to create fusion, so if we wanted to build a reactor that generates energy from fusion, we have to get clever. To date, scientists have invented two ways of making plasmas hot enough to fuse. The first type of reactor uses a magnetic field to squeeze a plasma in a donut-shaped chamber where the reactions take place. These magnetic confinement reactors, such as the ITER reactor in France, use superconducting electromagnets cooled with liquid helium to within a few degrees of absolute zero, meaning they host some of the biggest temperature gradients in the known universe. The second type, called inertial confinement, uses pulses from superpowered lasers to heat the surface of a pellet of fuel, imploding it, briefly making the fuel hot and dense enough to fuse. In fact, one of the most powerful lasers in the world is used for fusion experiments at the National Ignition Facility in the US. These experiments and others like them around the world are today just experiments. Scientists are still developing the technology. And although they can achieve fusion, right now it costs more energy to do the experiments than they produce in fusion. The technology has a long way to go before it's commercially viable. And maybe it never will be. It might just be impossible to make a viable fusion reactor on Earth. But if it gets there, it will be so efficient that a single glass of seawater could be used to produce as much energy as burning a barrel of oil with no waste to speak of. This is because fusion reactors would use hydrogen or helium as fuel, and seawater is loaded with hydrogen. But not just any hydrogen will do. Specific isotopes with extra neutrons, called deuterium and tritium, are needed to make the right reactions. Deuterium is stable and can be found in abundance in seawater, though tritium is a bit trickier. It's radioactive, and there may only be 20 kilograms of it in the world, mostly in nuclear warheads, which makes it incredibly expensive. So we may need another fusion buddy for deuterium instead of tritium. Helium-3, an isotope of helium, might be a great substitute. Unfortunately, it's also incredibly rare on Earth. But here, the Moon might have the answer. Over billions of years, the solar wind may have built up huge deposits of helium-3 on the Moon. Instead of making helium-3, we can mine it. If we could sift the lunar dust for helium, we'd have enough fuel to power the entire world for thousands of years. One more argument for establishing a moon base if you weren't convinced already. Okay, maybe you think building a mini-sun still sounds kind of dangerous. But they'd actually be much safer than most other types of power plant. A fusion reactor is not like a nuclear plant, which can melt down catastrophically. If the confinement failed, then the plasma would expand and cool, and the reaction would stop. Put simply, it's not a bomb. The release of radioactive fuel like tritium could pose a threat to the environment. Tritium could bond with oxygen, making radioactive water, which could be dangerous as it seeps into the environment. Fortunately, there's no more than a few grams of tritium in use at a given time, so a leak would be quickly diluted. So we've just told you that there's nearly unlimited energy to be had at no expense to the environment in something as simple as water. So, what's the catch? Cost. We simply don't know if fusion power will ever be commercially viable. Even if they work, they might be too expensive to ever build. The main drawback is that it's unproven technology. It's a $10 billion gamble, and that money might be better spent on other clean energy that's already proven itself. Maybe we should cut our losses. Or maybe, when the payoff is unlimited clean energy for everyone, it might be worth the risk. Videos like this one take hundreds of hours to make and are made possible by your contributions on patreon.com. If you want to learn more about global energy, here's a playlist about nuclear energy, fracking, and solar power. Let us know in the comments if there are other technologies you want us to explain.
The potential role of nuclear fusion in sustainable energy for the 21st century carbon constrained world. Since the 1950s, scientists aim to safely generate electricity from nuclear fusion, a process where energy input exceeds the output. And recently, on December 5th of 2022, researchers at Lawrence Livermore National Laboratory in California achieved a breakthrough. They were able to use lasers to trigger fusion in hydrogen atoms, producing more energy than they put in. So, for you to have a gauge on the topic, here are the pros and cons of nuclear fusion as an energy source. So, firstly, nuclear fusion is an abundant fuel supply, since deuterium, one of the core materials for nuclear fusion, can be extracted inexpensively, especially in seawaters. Secondly, there are zero greenhouse gases emissions since there are no carbon dioxides or other harmful atmospheric emissions from the fusion process. Which leads us to its inherent safety since there are no chain reactions involved. Unlike nuclear power plants, nuclear fusion reactors are not bombs, therefore, explosions will not occur. There is also minimal radioactive waste because fusion reactors produces inert gas and although they may produce radioactive materials, deuterium, its other core material, has a relatively short half-life. And in comparison to nuclear fission, which we will delve into later, nuclear fusion has a greater energy density compared to nuclear fission. Also, it is a steady energy supply since it is completely compatible with hydrogen economy since water splitting by using electrical energy is a long established technology. And finally, it provides global energy security from its abundance. And now for the cons. Firstly, there are technological challenges in this type of industries because we are far from perfecting it. And secondly, the cost is very high since we have materials that are not readily available on our planet. Number 3, our tritium supply. The other core material is very hard to come by. Although it is said that the radioactive waste from tritium is relatively low, it still has a span of approximately 12.5 years, so radioactive waste is still wasted on that time. And since the technology is not readily available, or it hasn't been perfected yet, it's far from commercial availability. Also, there is a competition on renewable energy since nuclear fusion is very expensive. There are other alternatives in getting energy. And finally, there are regulatory and safety concerns and public perception. As I've said, when we hear nuclear, we always think of the bomb. So it's a bit of a taboo. And for our next subtopic, we have the global, regional, and national policies on nuclear fusion as an energy source, which are primarily aimed at supporting research, development, and international collaboration in the field. So now we have the outlooks and policies on nuclear fusion energy. On a global scale, we have the International Thermonuclear Experimental Reactor, or ITER. We have International Atomic Energy Agency, or IAEA, the European Union's Fusion Roadmap, the United States Department of Energy's Fusion Energy Sciences Program, and the international collaboration agreements. On a regional scale, specifically the ASEAN, we have the ASEAN School on Plasma and Nuclear Fusion, or the ASPNF 2023, and Sokndai Asian School, which is headed by Thailand. We have the 41st ASEAN Ministers on Energy meeting, the second China ASEAN Forum on Peaceful Uses of Nuclear Technology, and the third Asian and Pacific Energy Forum. On the national scale, however, we have only a number of laws that govern this industry, specifically the RA 1815, which is an act to create the Philippine Nuclear Energy Commission to administer, regulate, and control the use of application and disposition of fissionable materials. Also, to authorize an establishment and administration of atomic energy reactor, and to determine the manner of development, use, and control of atomic energy to provide funds therefor and for other purposes. Also, we have the RA 5207, an act of providing for the licensing and regulation of atomic energy facilities and materials and establishing the rules on liability for nuclear damage and for other purposes. We also had the Philippine Nuclear Energy Program as well as the Philippine Nuclear Research Institute. Now we move on to the basic concepts and principles of nuclear energy fusion. The basic concepts and principles of nuclear fusion reactions will help us understand it in a molecular level. So, what is a nuclear fusion? So, in simple terms, nuclear fusion means replicating the sun's chemical reactions here on Earth, or bottling a star as it is often called, to produce energy. So, how does it work, if you may ask? Hydrogen burning starts with the fusion process in the stars creating helium. To make practical fusion energy, we need reactions between the lightest elements that also form helium. In fact, heavy hydrogen isotopes, deuterium and tritium, work better together for fusion. When they fuse, they produce more energy per reaction than two regular hydrogen nuclei. Because regular hydrogen has just one proton, deuterium has one proton and one neutron, and tritium has one proton and two neutrons. Also, fusion and fission reactions both release energy by tapping into something called binding energy, a fundamental property of atomic particles that holds them together efficiently. This energy can be set free through fusion or fission. The strength of this binding energy tells us how well the particles in the nucleus are held together. The plasma state. Usually, a plasma is a kind of gas where a good part of its atoms or molecules lost some of their electrons. These free electrons let plasmas carry electrical charges, and only in a plasma can self sustaining nuclear reactions happen. So, where do we currently stand in this? Scientists in over 50 countries study nuclear fusion and plasma physics. They've just reached a milestone by getting more energy out of a fusion experiment than they put in. They use various machines and methods for fusion, like accelerators, tokamaks, lasers, and advanced fuels. The previous group has reported on nuclear fission, which begs the question, what is the difference between nuclear fission and nuclear fusion? Firstly, nuclear fission powers plants to produce electricity by breaking apart atoms, which releases a lot of heat. And compared to nuclear fusion, similar to what happens in the sun, can give us the same heat as fission but without the waste. In fusion reactors, they slam together two light atoms, deuterium and tritium, with lots of heat and pressure. This makes a heavier atom, helium, and produces a lot of energy. Also, the main fuel for these reactors are deuterium, which is in seawater. In fact, experts say that just 1 liter of seawater can provide as much energy as 300 liters of oil. Looking back at the pros and cons slide, we could remember that there are more cons than pros on nuclear fusion. Nevertheless, why is it still being studied? Fusion has the potential to create much more energy from a small amount of fuel compared to fission energy, which is used in nuclear plants, and way, way more than burning oil or coal. Many fusion reactor designs in the works will use a mix of deuterium and tritium, types of hydrogen with extra particles. In theory, just a few grams of these ingredients could make a huge amount of energy, roughly as much as one person used in a developed country uses over 60 years. Right now, in the 21st century, what is our current problem? Right now, the main challenge is efficiency. Most of the fusion reactors we have today consume more energy than they generate. Since there are little to no reactors worldwide that has reached the point of producing more energy than it consumes, known as breaking even. However, there are frequent new breakthroughs, and the future is looking more promising than ever now that we have a breakthrough on December 5th of last year, 2022, where they used laser to trigger fusion in hydrogen atoms. So the input is much lower than the output. For our fourth subtopic, we have the state of the art and emerging technologies on nuclear fusion. Nuclear fusion is a cutting edge and complex field of research with many state of the art and emerging technologies aimed at practical fusion energy making a reality. Here are some of the key technologies associated with nuclear fusion, which will be further explained by Francine later on this presentation. We have the tokamak reactors, magnetic confinement, inertial confinement, fusion. These are technologies as mentioned earlier many times. The advanced materials for nuclear fusion, the fuel cycle and tritium breeding, the neutron activation and radiation shielding, remote handling systems, compact fusion concepts, advanced diagnostics, supercomputing and simulation, and finally the international collaborations for nuclear fusion energy.
To begin, let's consider the pressing need for nuclear fusion in our quest for sustainable energy. As we transition to renewable energy systems, fusion power plants play a crucial role in providing large scale energy storage capacity. This capacity is essential for a carbon free economy, enabling us to harness clean energy on demand, regardless of weather conditions or time of the day. Moreover, fusion technology contributes to nuclear non-proliferation by reducing the need of materials and processes that could be diverted for military purposes. So, in order to attain a carbon free economy, the current paradigm of nuclear energy, primarily based on fission reactors, relies on uranium and thorium as fuel sources. Until now, practically all nuclear reactors here have been light water reactors, which employ the hydrogen in the water to slow down the mega electron volt neutrons generated. So the reaction cross section for low energy neutrons significantly rises for odd atomic mass actinides, earning the term hot nuclear reactors. An LWR is normally fueled with approximately a ton of uranium 235 mixed in with about 24 tons of uranium 238, enriched to about 4% of uranium 235, and hence poses little proliferation concern unless the proliferator possesses isotope separation capability. So with this, there is also no possibility of criticality. So given the no criticality risk, each year a LWR is refueled and the reactor discharges its fuel and waste, which includes 24 tons of uranium 238, a 1% enrichment of uranium 235, 200 kilogram of actinides, and 700 kilograms of intermediate Z radioactive reaction products with a half-life of 30 years. The French use nuclear power for 80% of their electricity, and they do it without going bankrupt or destroying the environment. So, while both nuclear and solar electricity are anticipated to be viable, carbon free choices by the mid century, this actually believes that the existing data favors nuclear as the primary source. So, at the moment, Europe's gigantic laboratory proves this, which shows that carbon-free economy is actually attainable given how it is applied in France and is currently um, using it as their source of electricity. Furthermore, the French release far less carbon dioxide per capita into the environment than their German counterparts. In reality, despite the energy wind, the Germans continue to rely heavily on soft coal to generate electricity when the sun does not shine, the wind does not blow, or to replace lost nuclear power. The figure depicts per capita of carbon dioxide emissions for European nations, derived by dividing the BP's 2014 carbon dioxide emissions by the population at the time. Clearly, the average Frenchman emits half the carbon dioxide that the average German does. However, it's essential to understand that thermal nuclear reactors use only a tiny fraction of the total resource, well under 1% of the available uranium and thorium. So, in this sense, nuclear fuel is indeed a finite and diminishing resource. To meet the world's growing energy demand sustainably, we need more efficient and abundant sources, and actually, nuclear fusion holds the key. As we embrace nuclear fusion, we also contribute to global security through non-proliferation efforts. The proliferation of nuclear weapons and the associated risks are significant concerns. In the context of non-proliferation, we must address the use of neutrons to create fissile material, the leveraging of research on ignited, inertially confined plasmas for thermonuclear weapon development, the diversion of tritium for boosting nuclear weapons, and the diversion of materials for radiological dispersion devices. Fusion technology helps mitigate some of these risks, making it a safer choice for sustainable energy production. So in this slide, we can see the figure where the existing risks of the mitigation of the fusion power plant is then matched to the mitigated risks. So the process of generating special fissile materials involves the introduction and exposure of source material, which is also controlled material to fusion neutrons. After irradiation, the material is extracted. Detecting these materials is relatively uncomplicated with existing capabilities. So it's important to note that the primary focus of the non-proliferation regime is the detection of improper use of nuclear materials and is not designed to address scenarios of breakout. Detecting a breakout scenario early is considered a success of this regime, as it allows states to employ various measures to isolate and persuade non-compliant actors into compliance. So next, there are certain types of fusion, particularly inertial confinement fusion, as opposed to magnetic confinement fusion, aim to maximize fusion ignition for achieving high fusion gains. So some knowledge related to achieving such high fusion gains may have relevance to the development of thermonuclear weapons. So these weapons, a fission core initiates a compresses a deuterium-tritium plasma to extremely high density, utilizing inertia to confine the plasma for substantial yields. So lastly, there's a peripheral concern regarding the potential use of certain associated radioactive materials in radiological dispersal devices, or what we call RDDs, or we must also know as dirty bombs. So these dirty bombs, or RDDs, differ from nuclear weapons as they use conventional explosives to disperse radioactive materials across populated areas. Virtually all radioactive materials, such as cobalt 60, could be employed in an RDD. In the context of fusion, tritium, a fusion fuel or byproduct in most designs, could theoretically be included in an RDD in the form of tritiated water, or what we call H2O, directly, or in the elemental form of HT if the explosive device causes HT to oxidize into H2O. Now, let us discuss the environmental benefits of nuclear fusion. So, one of the key advantages of fusion is its minimal environmental impact. Unlike traditional nuclear fission, fusion reduces the risks of serious industrial accidents and does not produce long lasting radioactive waste. In a fusion reactor, only a limited amount of fuel, just a few grams, is present at any given moment. The process is inherently self limiting, meaning that the plasma actually is they naturally maintain stability. Even if a disruption occurs, the physics of fusion itself switches the reactions off. As a result, fusion technology avoids the production of long-lasting radiotoxic elements like actinides and other fission products, making it a cleaner and safer alternative. In nuclear fusion, the release of nuclear energy is similar to that in the nuclear fission power plant. So, however, fusion reactors introduce a key aspect of nuclear power, which is the inherent nuclear safety. So, this safety feature is rooted in the requirement for a coordinated interplay of multiple reactor technologies to maintain high temperatures and sustain fusion reactions. In the event of a failure in any of these technologies, the exposed components are subject to intense heat radiation. Currently, the anticipated lifetime of nuclear components is relatively short due to the high energy flux, primarily comprising intense neutron and heat radiation, which represents a significant technological challenge in the development of fusion power reactors. Economically, fusion offers numerous advantages. It relies on isotopes of hydrogen such as deuterium and tritium, which are widely available. The fuel supply for fusion is relatively inexpensive and stable, not subject to the price volatility and supply chain disruptions that can affect fossil fuels. This economic stability is a significant benefit for both consumers and industries, reducing uncertainties and risks associated with energy costs. The investment expenses for the Demo 2 model, considering 2015 pricing, are summarized in the table. These costs do not encompass financial factors like overnight costs. The model accounts for the expenses associated with implementing power plant technologies at continuously updated price levels. The cost breakdown follows standard accounting categories typically used in power plant cost reports. The component unit costs within the fusion power cores pertain to first-of-a-kind elements. So this means these items are presumed to be relatively costly to construct because they essentially serve as prototypes, and specialized tools and machinery may have been custom made for their creation. The cost of fusion specific technologies constitutes around 75% of the total direct construction costs of the plant, reflecting the lack of established expertise and the inherent production and commissioning risks. So the necessary funding, approximately $141 per megawatt hour, is comparable to the subsidies provided for offshore wind energy, which amounted to $136 per megawatt hour in the Europe in 2012 at 2015 price levels. So these costs, as seen in the table in this slide, are substantially lower than the subsidies granted in the same year for photovoltaic plants, which reached $249 per megawatt hour in 2015 price terms. It's worth noting that these renewable resource subsidies do not encompass the expenses linked to maintaining large standby power plants running on coal, gas, or pumped hydroelectric stations, which fusion plants will not require. In summary, compared to these renewable resources, fusion power plants can generate electrical energy safely in a more environmentally friendly manner and at a lower cost as assessed. So, the reliability of the presented findings is closely tied to the accuracy of the input data used for the demo model. So, conceptual design activities are currently underway, and the model's cost estimates represent a preliminary approximation. Some of the uncertainty is mitigated by incorporating standardized, proven non fusion technologies. Leveraging the experience from operational nuclear power plants reduces the technical and economic risks, drawing from the wealth of technical and economic knowledge available. And now let us delve into some of the research and development opportunities that we have currently in the industry of nuclear fusion as a future energy source. So we have three, which is first the advanced plasma confinement and heating techniques. Next is our tritium breeding, and lastly, the modeling and simulation. So these are one of the three research and development opportunities we have in the world, but these are not limited. But these are basically the main ones that we focus now, especially the advancement of technologies happening in the world. So, advanced plasma confinement and heating techniques are fundamental to achieving the conditions necessary for fusion reactions. So, researchers have explored magnetic confinement utilizing strong magnetic fields to contain and heat the plasma. A prime example is the tokamak, a donut shaped device that uses a combination of toroidal and poloidal magnetic fields to stabilize the plasma. The ITR project stands out as a prominent tokamak experiment. So, another approach is the inertial confinement fusion, or the ICF techniques, involves rapidly compressing a small fuel pellet with intense energy from lasers or ion beams. So, the National Ignition Facility in the United States is an example where lasers are used to achieve the necessary pressures and temperatures for fusion. Then, lastly, the accelerators represent an alternative magnetic confinement approach designated to maintain plasma stability without the end for a toroidal current. So, the Wendelstein 76 project in Germany is a significant endeavor in this category. So next is we have the tritium breeding. So tritium, one of the fusion fuels, is not naturally abundant and must be bred within the fusion reactor itself. Researchers achieve this by radiating lithium blankets with neutrons produced during the fusion reaction. For example, in a deuterium tritium fusion reaction, lithium 6 can be used as a breeding material where lithium 6 captures neutrons and transforms into tritium. Researchers are continuously working to develop innovative blanket materials and designs to enhance tritium breeding efficiency while minimizing the release of tritium, which is radioactive. So, a well designed tritium breeding system is crucial for sustaining the fusion fuel cycle. Lastly, modeling and simulation plays a vital role in the development of fusion technology. So these tools are used to understand and optimize various aspects of fusion research. They help us comprehend plasma behavior, reactor design, and the intricate interactions between plasma, magnetic fields, and reactor material. So examples include the gyrokinetic code or gyro, which models plasma turbulence in magnetic confinement devices, aiding in the prediction and control of plasma instabilities. Multi-physics simulations enable the study of the structural integrity of reactor components under extreme conditions, helping to ensure safety. So, these modeling also plays a crucial role in optimizing the magnetic confinement geometry in devices like tokamaks, improving plasma stability and heating efficiency. So that
So
is
that is
all for
all for
our
our
presentation on
presentation
nuclear
of
fusion
the
as
nuclear
future energy
fusion as
source.
future
Thank you
energy
very
source.
much
Thank you
for
very much
listening.
for listening.
So that